Yeah, good afternoon. Today's class is the second class on joining processes. So last on that class we discussed about fundamentals of welding. Then we discussed about liquid welding processes. So as I told you in the beginning in the first class that in this course I am going to cover fundamental of welding, liquid state welding processes, solid state welding processes, liquid solid state based welding processes, and welding defect analysis. Okay, so on today's class, I'm going to cover the remaining part of the fusion welding process or liquid state welding process, that is resistance welding, and then I will discuss about solid state welding. This is the content which I have already told in the previous class. If you see the contents, it contains 5 parts. One is fundamentals of welding, which I have already covered last class. Then second part is liquid state welding processes. This one also I covered last class. In today's class, I am going to cover this one, solid state welding processes, and remaining part of liquid state welding process. Remaining part is resistance welding and remaining part of liquid state welding process. So what is resistance welding? In a resistance welding, what happens is, so before starting today's class, I would like to answer your queries if you have any. Anybody is having any query based on the last class lecture? So anybody want to ask any questions based on my last lecture? If there is no query, I will start today's lecture. The first topic is part is resistance welding. Resistance welding is also a part of fusion welding process. As I discussed in the last class, fusion welding is coming under liquid state welding processes. Under fusion welding, there are 3 types. One is arc welding, second one is first one is gas welding, second one is resistance arc welding, third one is resistance welding. Last class we have already covered the details about gas welding as well as arc welding processes, and today's class we are going to cover the resistance welding process, which is also part of a fusion welding. So in resistance welding, what happens? Generally resistance welding is mainly used for resistance spot welding. Resistance spot welding is mainly used for joining 2 pieces in lap configuration. Mainly this process is used for thin metals. If your metal and your material should be metallic in nature. So if you have two and you can only join in lap configuration. As we discussed last class, what is the difference? We have already discussed the difference between butt welding, lap welding, T-joint and all in the last class. Resistance welding can be only used in lap configuration, resistance spot welding. So if you see the heat produced by resistance welding is heat equal to I square RT. Because of Joule heating, it gives heat. So here heat source is Joule heating, so heat equal to I square RT. So R is your resistance, I equal to current, and T equal to time, and K is the loss factor. So in heat, heat produced by resistance welding is related to square root of current, square of current, resistance and time. Resistance welding is a very quick process. Generally in all the automotive sector, mainly this welding is mainly used in automotive sector, where there are thousands of parts to be joined, and it has to be joined very quickly. So here main advantage is it's a very quick process, and the time consumption for heat resistance one resistance welding can happen in less than a second. So it is that fast process. So to reduce time, heat equal to I square RT, and I equal to current, so R equal to resistance, and T equal to temperature, T equal to time, and K equal to your loss factor. So the process variables are this current, time, and force. Force will also come to picture. I will tell you in detail. So because of this, what happens? Your objective is to improve, give high heat input. Because of heat only, the welding will happen at the two interface. So to provide more heat, you have to give high current here, because your time is very small. The main objective is that in resistance welding, welding happens in a second. So very short, within very short time. So to reduce the time, but you have to generate that much of heat to weld the material. So current will be very high. Here the current is very high, in the order of around 15,000 ampere. and voltage is very less. Voltage you have to apply very less voltage, very high current, and now your heat is depending upon current, how much current you give, that is in your control. You have to give current in the order of 15,000 ampere, and you need to do it very less time, so you have to give high current. And resistance. What is resistance? Resistance is like when you join two pieces together, what happens here in this process? In this process, you have to place two plates together. The two plates to be joined will be placed together. Then on top of the one plate and bottom of the one plate, two electrodes are there. Two electrodes are there. Electrode and electrode. And this is your workpiece one. Workpiece. So now what happens? While how welding happens? Initially, what you have to do? You have to place two workpiece like this, or in lap configuration, you have to place two workpiece like this. Then on top of and in both side, you have to use two electrodes. Electrode 2. You have to use two electrodes on top and bottom side. Then what you have to do? Then you have to apply force. You have to apply heavy force. So because of force, what will happen? As we know, any welding process, for any kind of welding to happen, you need to maintain material continuity. That's what I discussed in the previous class. So to maintain material continuity, you have to apply force. When you apply force, these two, there will be no gap between the two pieces. It will reduce the gap. And under high force, what will happen? When you apply current, when you apply high current in the order of 15,000 ampere, at that time what will happen? Then resistance. So your heat will be developed at the intersection. Heat will be developed throughout, because wherever resistance is there, heat will be developed. So where resistance is there, resistance will be there. One resistance will be there here. You have one resistance here in this electrode. When current will pass, here this is one resistance. This is second resistance on the workpiece, and this is the third resistance at the intersection. This is the fourth resistance at the workpiece below lower workpiece, and this is third resistance, the electrode which is connected to the lower part. So there are how many resistance? Resistance 1, 2, 3, 4, 5. So 5 resistance is acting together, and you will have heat in each place, because heat equal to I square R. But your objective is to induce heat only at the interface. Only at the interface you want to induce heat. That's why in order to increase heat, you have to increase the contact area at this zone. That's why this area, contact area, is more, and the remaining area you have to reduce the size as small as possible, because you don't want heat here, you don't want heat here, heat to induce here, you don't want here, you don't want here, but you only want in this zone. That's where you have to design your electrode and electrode setup in such a way that in other places you will not get any heat. Heat will also induce at the interface. Okay, so that is the main objective here. And in resistance welding, what happens? So that's why, what are the process parameters? Process parameter is current, because heat equal to I square RT. Then the resistance is also a process parameter. Then time, at what time it is happening, that is a process parameter. And then force, because you are applying force as well. So force also you are applying, so it is also a time process parameter. Now what should be the then when you join two pieces together, the one beauty of resistance spot welding is, like, you can join two pieces of any size. The top piece may be of thicker size, bottom piece may be of thinner size, or both may be of same size, or bottom may be of thicker size, top may be of thinner size, or both may be of dissimilar materials. One may be aluminum, second one may be copper, or one may be but it should be metallic materials, conductive materials. Okay, if you want to join two dissimilar materials, one material will have one property, second material will have another property. Suppose you want to use aluminum with copper or aluminum steel. Aluminum will have some thermal conductivity, steel will have some different thermal conductivity, or aluminum will have some electrical conductivity, steel will have some other electrical conductivity. So, and aluminum will have some melting point, steel will have some melting point. So even though both are dissimilar, you can easily do by using resistance spot welding. But the main part is you have to control the heat balance. Heat balance is very, very important. You have to provide the heat input in such a way that fusion will happen at the interface. For example, suppose you want to join one thick workpiece with one thin workpiece. Then how will you balance the heat? To balance the heat, what you have to do? Towards in the thick side, which is your control? Your control is only electrode workpiece. This area is under your control. To control the heat, what you have to do? So to thicker side, you have to use a thicker electrode, and to thinner side, you have to use thinner electrode, because you want to balance the heat input. For example, suppose you have two materials of different thermal conductivity. So one is of high thermal conductivity, and this is a how will you connect, how will you give your provide electrode? If it is, since it is of high thermal conductivity, so in this case you have to use by giving less area of electrode also, it will able to transmit the heat in a faster way. So for the material which is having high thermal conductivity, you have to use smaller area of electrode to balance the heat, and the material which has low thermal conductivity, there you have to use a electrode with bigger area. So like that you have to balance the heat for while doing resistance spot welding. The next parameter is electrode. So what is the function of electrode? The electrode, this is one electrode, this is one electrode. What is the function of electrode? The function of electrode, you have to select your electrode in such that what electrode does? Electrode transmits the electricity, first thing. Second, you have to apply force through the electrode. It means the electrode should have very good electrical conductivity as well as thermal conductivity. The electrode should have very good electrical conductivity, because it should transmit electricity. And second objective is the electrode should be as strong, very high strength. It should have very high strength or hardness, because we have to apply force, and whole process will happen under the application of force. That's why the electrode should sustain that force application. That's where different electrodes are. So if you see the conductivity, first objective is that electrode should have high conductivity. So copper is having very high conductivity. So copper is a suitable material, but even though copper is having high electrical conductivity, the strength of copper is very low. So that's why copper is not even though from electrical point of view it is ideal candidate, but for strength point of view it is not an ideal candidate. If you take steel is of having very high strength, so it satisfies the second requirement, but steel is also having low electrical conductivity. So steel is also not an ideal material for this one. That's why they use copper alloys such as copper chromium alloys. So by adding chromium, they increase the strength of the copper, and even though it increases strength and with little bit decrease in electrical conductivity. So copper chromium alloy gives very good electrical conductivity and very high strength. That's why they use mainly copper chromium alloys also for electrode material. Now how the welding is happening actually in a electrical resistance welding process? It's a spot welding process. As I said, there are two electrodes, and you have to place the workpiece in lap configuration. Then you have to select your electrode in such a way that the cross sectional area should be as small as possible, so that resistance, you want high resistance only at the intersection, you don't want resistance at other places. That's why you have to design your electrode accordingly. Then what you have to do, you have to apply pressure. So what will happen, you can see at the interface you will have something this kind of intersection. So because of this high pressure, high current, first melting will happen here. Within fraction of second, melting will happen here. Once it melts, the remaining other part will also join together. So that part will melt. Like that, whole part will melt it, and you will get a joint together. What happens actually in this electrical spot welding? What you have to do? Resistance welding. You have to place workpiece in this fashion. Then you have to place your electrode 1, electrode 2 like this. Then you have to apply force in the second step. You can see apply. You have placed two electrodes together and you have applied force. You can see this force versus spot welding cycle time, force versus time. After some time you are applying force. So here only in this stage you have applied force. Then here what will happen? Here you have to supply current also. So you have to apply force, and here you have to apply current. So this is the for force and this is for current. So when the force will be high enough, what is the objective of force? It will make two pieces in such a way that it is to, by applying force you can make keep both pieces together as possible, as close as possible, so that so that it will maintain the material continuity. Okay. Then when it will maintain the material continuity, then you have to apply force, current. When you apply current, what will happen? Then here you have applied current as well. So current will be applied under the application of force. Then what will happen? So then what will happen? Now you are applying force also and current also. So this area will be melted. When something will be melted, you are further still the force will, what the force will do? It will bring the top part down and it will move the bottom part up. So as a result, and the other part will also come in contact with each other. And since whole thing is happening under process, under force, then what will happen? You will not get any porosity in a resistance welded material. So it will be kind of porosity free. It is a quick process, and since whole process is happening under the application of load, then it will not have any porosity in the material. So this is about electrical resistance welding. So you can also transmit that electrical this principle for continuous welding like seam welding. What you can do in this one we discussed like resistance spot welding. You can also get something like resistance seam welding, where what you can do, you can use this resistance welding in a rolling mill. What you do, connect the top roller to one electrode, because roller material is also conductor of electricity. So bottom roller also you connected to electricity. Then what will happen? Then you use the same process. Roller will be rotating and it will give spot welding continuously. Here one spot welding, here one spot welding, here one spot welding. Like this you can do continuously, because it is a continuous process. Roller will be rotating in some direction, and so it will drag the workpiece from, or in this case roller is rotating like this, so that workpiece is dragged in this direction. So you will get a continuous welding in this case. This is called a seam welding. You can also do for continuous welding, you can also do projection welding. What you can do, you can create your material workpiece in this fashion. You can create your workpiece like this. Then you place your workpiece between two electrodes. Then you apply high current, so it will melt, and it will, in this area you will join. So in this, like this, you can make continuous welding. Not only this spot welding principle can be used to make either seam welding or projection welding for having continuous welding in a thin between two thin sheets. This is about resistance welding. So now we completed the fusion welding processes. In fusion welding, so this is the application of resistance spot welding. You can see around 80% automobile body panels, 80% of welds are made by resistance welding. You can see the photographs like BMW car, BMW, Skoda, Hyundai, Mercedes Benz, Nissan, everywhere they use more than 80% of parts of these vehicles are made by electrical resistance welding. We also use a lot of lot of weldings are happening in other applications as well, like aerospace applications, railway, space, sports, medical industries, computer applications, structural components. Many places they use electrical spot welding. In our household applications also we use electrical resistance spot welding, such as in fridge racks, doors, air conditioning units, gas stoves, washing machines, and everywhere they use electrical spot welding, because it is a very fast process and it is a very quick process. But what is the limitation here? What are the applications, advantages and disadvantages of electrical resistance welding? The advantage, main advantage is it is a quick process, very quick. First advantage is very quick process. Second one is it can be automated, so it is very for mass production. Mass production can be done very easily. So third point is it can be automated. So fourth is no consumable gas. Shielding gas is not required. No consumable gas. Fifth advantage is you don't want any filler material as well. No filler metal. These are some of the advantages of the resistance welding. What are the disadvantages? The disadvantages are, the main disadvantage is that we can only join thin pieces, thin plates. thin sheets. What is the second disadvantage? The second disadvantage is only lap configuration. Okay, so these are the two major disadvantages of the resistance, advantage and disadvantage of resistance spot welding, and it has huge application. We discussed in this slide. It has lot of applications. So we finished the fusion welding processes. On fusion welding process, what we did, we discussed first, before starting the fusion welding, we discussed like in what condition we can do joining, what is the requirement for joining, required conditions for obtaining a good joint. Then we discussed about arc welding. Then we discussed about fusion welding or liquid state processing process welding. We discussed that there are four kind of fusion welding processes. First kind is gas welding, second kind is arc welding, third kind is high density welding, fourth type is your resistance welding. Last class we discussed about gas welding, where the heat is produced because of combustion of gas. We discussed about oxy-acetylene gas welding. Then we discussed about arc welding. We told that the principle of arc welding is same, and then depending upon your need, you can use a particular type of polarity and you can develop any kind of arc. We discussed how an arc can be developed, and then we discussed that arc weldings processes are classified into two types. One is consumable based arc welding processes, second one is non-consumable type arc welding processes. We discussed few type of consumable type arc welding processes such as shielded metal arc welding. Then we discussed about flux core arc welding. Then we discussed about submerged arc welding. Then we discussed about gas welding. So then we discussed about non-consumable type arc welding. We discussed like what is the difference between consumable type and non-consumable type arc welding processes. Under non-consumable type arc welding category, we discussed about gas tungsten based arc welding process, and second category is plasma based arc welding process. Then we discussed the difference between these two. Then we discussed about high density based arc welding process. We discussed about electron beam welding, and we discussed the electron beam welding, the thickness to diameter ratio will be very high. You can even join to very thick material. Around, if the ratio is 25:1, then also you can join two materials by using electron beam welding. And there we discussed that in electron beam welding, the power density is very high. We also discussed like how can we classify all the welding processes based on arc welding process based on power density. That also we discussed. So then today's class we discussed about resistance welding. In resistance welding, what we understood is by using resistance welding you can join only thin pieces, but it is a very quick process. It can be automated, and largely this process is being used in automotive sector. Okay, so we discussed here the heat source is because of Joule heating, I square R. So that we finished now. Now we'll discuss about solid state welding process. Before that, we will do analysis. Power density analysis of heat analysis of welding processes. What we discussed? We discussed gas welding. Then we discussed mainly arc welding. Third, we discussed resistance welding mainly. Okay, so now what we discussed again, the welding processes can be classified based on power density. What is power density? Power density equal to one is power density. So power density, which is nothing but power by area. Okay, so we can also define the heat input based on what? Heat input. What is heat input? As you know, it may be arc welding or resistance welding. You are giving some heat input. What is that heat input? That is, if it is arc welding, heat input equal to VI, power, whatever you are giving. If it is resistance welding, that is I square RT. That is your heat input. So heat input equal to heat equal to or power power equal to, or heat supplied, net heat supplied equal to P equal to either Vi or I square RT depending upon the welding process. Now, when you through the motor or through your setup, you are giving this much of, supplying this much of power, but there are so many losses. So then what are the losses? So then power available at the tip equal to, what are the losses? There are different type of losses. What are those losses? Transfer losses and many types of losses are there. So when heat will be transmitted, this is your electrode, right? So when heat will be, the power supplied will come here of the tip of the workpiece, tip of the electrode. So now it has to be transferred from this tip of the electrode to the workpiece. So in between there will be so many losses. So those losses will be accounted by transfer efficiency. So transfer efficiency equal to output by input. So what is your input here? Any efficiency is nothing but efficiency equal to output by input. Here which is your input? Input is your, this is your input. So the heat which is available at the tip. So heat supplied by, so heat input equal to heat available for weld. Heat supplied, which is nothing but heat available at the electrode tip. What will be in the top side? It will be efficiency equal to heat available for welding by heat available for at the tip. So that is your transfer efficiency. So heat available for welding. Which is nothing but output by input. Okay, which is nothing but your output by input. Now what is heat available for welding? Then heat available for welding equal to heat available for welding. You can tell as net heat input. Net heat equal to what? Net heat equal to efficiency into what? Heat supplied, Vi. Okay, so this is net heat. So net heat equal to what we got? Net heat equal to efficiency into power, or Vi, or this is nothing but Vi or I square RT. Now this is about net heat. So now actually in welding we use heat input, not heat. So what is heat input? So in welding we use heat input, not heat. What is welding? What is heat input? Actually in welding what is happening? Whatever heat you are giving, that is that much of heat is not coming to the workpiece. Okay, because your electrode is moving. For example, let us take a candle and use your hand. You slowly move your hand. What will happen? You will get a level of sensation of heat. Okay, you first move your hand very fast against the candle. What will happen? You may not sense any heat, right? Now what you do? You slowly move your hand on the candle, burned candle. So what will happen? What will happen? So you may get heat, sensation of heat when your finger will touch the fire. Now you very slowly move your hand towards the candle. What will happen? You will get more sensation of heat. That's why the heat, however, the heat input, heat for developed by the candle is constant. Heat developed by the candle is constant, but depending upon the movement of my hand against the candle, I am getting a kind of heat sensation. Okay, same thing is happening in the welding. If you reverse that candle downwards, and if you assume that your candle is your electrode, and you assume that your hand is workpiece, then if you move electrode against the workpiece, if you move the electrode against the workpiece at a fast rate, then what will happen? The workpiece will not get high level of heat input. And if you move the electrode very slowly, then your workpiece will get more heat input. That's where only the net heat is not enough. You have to give heat input. So heat input equal to power by velocity. Okay, or heat supplied by velocity. So in welding, they instead of using heat, net heat, they use heat input. Heat input equal to power by velocity. So what is the unit of power? That is nothing. Power equal to watt. Watt is nothing but Newton meter per second. That is joule per second. Joule per second by mm per second, right? So you that is about heat input. Okay. So similarly here, net heat input equal to, now we got net heat for welding. So what is net heat input for welding? Equal to same thing, efficiency into power by V. Not only power, power by V. Here this power may be VI or I square RT. This is heat, net heat input for welding. That this one we got. We consider the transfer efficiency. Now this much of heat is available for welding here. This much of heat is available for welding here. We have taken care of the losses. What are the losses? The conduction, radiation, heat will be lost into various convection, through convection, radiation and all. Now heat is available for melting. Now what is happening? Heat is available. This much of heat is available for melting. But whether this much of heat is whether this is available, but how much heat is utilized for welding? So this much of heat is available for welding. So now we are here. This much of heat is available for melting. How much heat is utilized for melting? That will be given by melting efficiency. Melting efficiency equal to input by output. What is input? This is your input. This is your input. Okay, net heat input for welding. What is your output? How much heat was really utilized for welding? Heat, actual heat utilized for welding. This is melting efficiency. So I will repeat again. When you supply a when you give a supply, it may be resistance welding or electrical arc welding. When you apply some current or voltage, then what will happen? The heat will be developed. Like it may be VI or I square RT, depending upon whether it is arc welding or resistance welding. Then that much heat will come up to the tip of the electrode. Then when now this heat has to be transmitted from here to here to workpiece. So in between there are lot of losses. So this is called as transfer efficiency. That's where transfer efficiency equal to heat available at the tip of the any efficiency equal to output by input. For calculating transfer efficiency, this is your input, this is your output, and this is your input. So transfer efficiency equal to heat required for melting by heat available at the tip of the melting. So this heat available at the tip of the melting is VI or I square RT. So transfer efficiency equal to this heat by this heat. So therefore this heat equal to, this heat may be called as net heat for welding. Net heat for welding efficiency into P. Now we should not consider only heat, because in a welding we, instead of using heat, we use heat input. Heat input is, sorry, this is HCAT. Okay, so heat input equal to power by V. So net heat input equal to efficiency into P by V. Now we supplied heat up to here. Now it has to go inside. So in out of that heat, how much heat is utilized for welding? That will be given by melting efficiency. Melting efficiency equal to net heat input, which we have calculated here, actual heat utilized for welding by net heat input. That is your melting efficiency. Okay. So using this, can you solve this problem? Yeah, quickly do. So I am giving you 5 minutes time, and try to solve this problem. It's a very simple problem. Try to do it. So the one student candidate asked, like, sir, what is the ampere required for resistance welding? It is around more than 10,000 ampere. So it is around 15,000 ampere. What are the parameters affected for resistance welding process? The parameters are, as I said, power equal to I square RT. So parameters are current, resistance, and T, temperature, time. and it also you are applying force, no, force is also a parameter. So have you done solve this problem? The question is, consider a situation where a welding operation is performed with V equal to 20 volt, I equal to 200 ampere. The cross sectional area of the weld bead is 10 mm square and the electrode moves at a speed of 10 mm per second. If the heat required to melt is 20 joule per mm³ and heat transfer efficiency is 0.9, estimate the melting efficiency. It's a straightforward question. Kindly do it and tell me the answer. Anybody has done? Yeah, so somebody asked, like, can we do gas welding in vacuum to avoid defects? Yes, you can do, but it's a combustion. Gas welding is a conventional welding, no? Why do you want to use in vacuum? If you want to do in vacuum, do a high-end welding process. Gas welding is generally used for example, our grill and all. We use gas welding, no? Because we use gas welding because it's a time-saving process and it is a easy process. Air gap plays a major role. That's why only you are applying pressure in both sides. Somebody asked that does the air gap between workpieces play any role? Yes, it plays a major role. So to avoid that, you are applying force in both sides so that there will be no air gap and there will be material continuity, and then you can apply current, and so resistance will happen. Heat will be developed and welding will happen. So what is the answer? Anybody is done? So please solve it. What is the answer? So here voltage is given, current is given, voltage is given, current is given. So and efficiency is given, transfer efficiency is given. So efficiency transfer equal to what? Net heat supplied by total power heat input, isn't it? So what is net heat supplied? Net heat supplied equal to 20 into V into I, 200 into 0.9 equal to what? You know net heat supplied, how much? Tell me, what is this is net heat supplied, then what is the heat required to melt? Heat required to melt equal to what? 20 is your joule, 20 joule per mm³, 20 into area, that is 10 into 10. So 20 into 10 into 10 equal to what? 2000 joule per second. This is what heat net, you know, net heat supplied, heat required to melt, you know. What is this answer? What is this value? Anybody has calculated? Yeah, total answer is correct. This is around, what is this one? You have to calculate and tell me. It will be around 3600. So then melting efficiency equal to 2000 by 3600 equal to 55%. Yeah, you are correct. Somebody has calculated as 55.6. Similarly, do this problem. Do it quickly. Consider a situation where a welding operation is performed with V equal to 20 meter per 20 volts, I equal to 200 ampere, and the cross sectional area of the weld bead is 30 mm square. Estimate the welding speed if the workpiece and electrodes are made of aluminum. Use an efficiency of 75% and specific energy required is 2.9 joule per. Please do it quickly. In interaction, Rohit said, is liquid state welding in liquid state, if filler material is not same as base material? Yes, it is up to you. Mostly you have to use same filler material like your base material. Otherwise also it is okay, but it will become an alloy at the interface. So then Rohit asked, sir, how can we reduce heat affected zone in oxy-fuel gas welding? You cannot reduce heat affected zone in oxy-fuel gas welding. You will definitely have a heat affected zone. It is very difficult to control heat affected zone in a oxy-fuel gas welding. For that, if you want to control, you have to change your welding process. Maybe resistance welding or like solid state welding, which we are going to discuss today. Yeah, what is the answer? Please tell me quickly. Yeah, please tell me quickly. What is the answer? So it is a very simple question. Your voltage is given, V is given, I is given. You can easily get your input, initial input, which is nothing but V into I. So you will V into I equal to something around 20 into 200 equal to around 4000 watt. So efficiency equal to output by input. What is your net heat input? Net heat input equal to 0.75 into 20 into 200 will give you net efficiency 75%. So what is required? Heat required. So this is net heat input. So this is nothing but around 3000 joule per second. What is the heat required to melt? He has given specific energy equal to 2.9 joule per mmq. What is the heat required for melting? Therefore, heat required for melting equal to what? 2.9 into volume, because joule per mmq 2.9 into area 30 into V. Much of heat is required for melting, and you are supplying net heat to this much. So 2.9 into 30 into V equal to 3000. I am asking what is V? Tell me what is V? What is V? Yes, 34.5 mm per second. So your V equal to 34.5 mm. So with this, now we completed the fusion welding process. And now let us, many students asked how to control heat affected zone and all. I will discuss here limitation of fusion welding process. In all the fusion welding process, whatever you use, the main first limitation is heat affected zone. Okay, so whatever you do, you will have a bigger heat affected zone. Suppose you want to join this is your joint region, and this is your heat affected zone. Heat affected zone. You cannot control this heat affected zone because you want to melt your molten metal. So the higher the molten temperature of your molten metal, you will have bigger heat affected zone. So you cannot control heat affected zone problem. And this is your undesirable condition. This heat affected zone is an undesirable one. So for example, if you see an iron carbon phase diagram, your iron carbon phase diagram is something like this, right? So in iron carbon phase diagram, if you melt and solidify, you in many cases you will get austenite. This is your 2.14% carbon. This is carbon, and this is temperature. And this is your melting point. Suppose your alloy is somewhere here. This is your gamma phase. This is liquid. Yes or no? And here you will have many. There are many phases. So here you will have eutectic again, something like this. So there are many phases. So any case during your heat cycle, your phase may be here or here or here. Depending upon that, so you will get. So if your phase is somewhere here, so here you will get a pearlite microstructure. What is pearlite microstructure? Your microstructure will look like something, or if in a eutectoid composition, you will get a eutectoid microstructure. Suppose your microstructure is eutectoid, you will get something this kind of layer structure. If your microstructure is austenite, you will get a austenite grains only. So depending upon your heat treatment cycle, so because of the melting point of aluminum is around more than 1550 degrees centigrade. When you heat it at one condition, you will get gamma, and in one condition you will get pearlite. And if your heat treatment, so here you may get the temperature in this zone, either in this zone or in this zone. If depending upon this zone, your material property will affect. So for example, if you have this kind of microstructure, it is a ductile material. If you have this kind of microstructure, you will get high strength material because it is a pearlite structure. You have cementite ferrite, like this layered structure. So depending upon that, your mechanical property changes. So heat affected zone is a undesirable condition for any material. So you cannot avoid in any kind of fusion welding process. This is the biggest disadvantage. What is the second disadvantage? In fusion welding, what happens? You are melting and solidifying this region, melting and solidifying. In melting and solidifying, what happens? It is a casting related work. In casting also you do melting and you do solidification. Because of that, what will happen? As we discussed in the previous class, because of this melting and solidification, you got in any, if you see any cast product, you get lot of blowholes, porosities, pinholes, inclusions. All the things are available, are seen in a cast product. Since here also in the weld zone is like your cast product. So you will also get similar kind of defects like blowholes, porosity, pinholes, inclusions. That's why you have to use proper shielding gas. Even though whatever shielding gas you use, still you get this kind of problems. Inclusion means if some oxidation will happen, oxide particles will be there in the inside the weld pool, then you will get inclusion. Blowhole means, as I said, there are so many atmosphere, so many gases are there. For example, if you take hydrogen, hydrogen has very limited solid solubility and very high solid solubility. So whenever hydrogen will come in contact, then in liquid state it will be absorbed, and in solid state it will come out. So as a result, it will give porosity. If the porosity size is big, then it is called as blowhole, and if the porosity size is small, it is called as pinhole. So like this kind of defects you may expect in any fusion welding processes. Next one is residual stress and distortion. What is residual stress? In welding, what you do, if you join these two pieces together, depending upon the melting point of the material, you have to melt this particular region. Our other part in the welding, this part, so this part is getting very high temperature up to melting point, and this region is at room temperature. So what will happen? So in a metallic material, one part, suppose it is steel or something, the melting point is up, that is around 1600 centigrade. So here you are heating that material up to 1600 degrees centigrade, and you are suddenly cooling, and this region is getting a temperature of around room temperature. And because of that temperature difference, the material will get what? If you heat anything to high temperature in open atmosphere, what will happen? It will try to expand. If you cool something, it will try to contract. Now, if you will tightly hold and you will not allow that for heating or cooling. So suppose you want to do welding. For welding, you are fixing your two workpieces first. So you are fixing for welding. You are fixing. So suppose you want to join two pieces together. First, you are fixing. Then you are moving your electrode in this direction, and then you are getting joining like this. So what will happen during melting in this zone? Suppose it is steel, it is getting a temperature around 1600 degrees centigrade. So because of this heat, what will happen? This adjoining area will try to expand, but you have held this one very tightly. So it is trying to expand, but you are not allowing it to expand. Or during cooling, what will happen? It will try to contract, but you are not allowing it to contract. As a result, the material will get residual stress. If you allow, then distortion will happen. If you don't allow, then it will generate residual stress. So any material will have residual stress if you do thermal cycle. If one part will get high temperature, other part will get low temperature, then definitely residual stress will be developed. And the order of residual stress development depends upon like what is the temperature of usage. So for fusion welding, since you are melting and solidifying, so the order of difference in temperature is very, very high. So there is a high chance that you will get high level of residual stress. However, when you come to solid state welding, you are not melting the workpiece to melting point of your material. So as a result, what will happen? Your order of temperature difference will be very, very low. So in case of fusion solid state welding, the level of residual stress will be very, very low. Here you will have very high level of residual stress. So what is the next limitation? Next limitation is not suitable for edge hardening alloys. What do you mean by edge hardening alloys? I have already given this example in the previous class. For some alloys like aluminum, a particular grade of aluminum alloy like aluminum copper alloy, or like 2000 series, that is called as 2000 series alloy, or 7000 series alloy, or 6000 series alloy. 6000 series is aluminum, magnesium, silicon alloy. Anyone, this is aluminum copper alloy, this is aluminum zinc alloy. Okay, so these materials are called as edge hardenable materials, and these materials are mainly used for these two materials, first one and second one. These are extensively used in aerospace structures, and the third material 6000 series is mainly used for automobile, and the first two are used for aerospace. Why they are using in aerospace? Why they don't use pure aluminum, but why they use? And if you see the cost, if the cost of aluminum is 1 rupees, then the cost of this one will be around 20 rupees, 20 times to very high costly. Okay, and people are still buying these materials even though these are very high costly, because aluminum gives lightweight and aluminum gives generally low medium moderate strength. But for this particular alloys 2000 and 7000 series, this particular metal gives very high strength. So that's why, and obviously, like naturally aluminum is having very low weight, so they use by getting lightweight and high strength condition, and they purchase aluminum 2000 series and 7000 series. What is 2000 7000? Why it get high temperature? Because they give a particular type of thermal treatment for this alloy to obtain that high strength. That treatment is called as edge hardenable for this material. What is edge hardenable? This particular metal gives this kind of phase diagram. This kind of phase diagram. If you see what they do, they heat the material from room temperature to a temperature where it will form single phase. So this is your single phase. This single phase alpha, you can see, and here it forms two phase alpha plus CuAl2. So if you heat somewhere here, then you will get a single grain solid phase. Since it is a single phase, you will get only grains. You can see this is a grain, alpha grain. There is nothing inside the grain. Now if you slowly cool, what will happen? Then on alpha grain you will get this kind of solid. On alpha grain you will get this kind of beta particles. Now if you not slowly cool, if you quickly quench it, so heat it and quickly quench. So heat to obtain. What they do? So they heat to obtain single phase, that is called a solution treatment. This ST means solution treatment. It means they heat to obtain single phase, then they quickly quench, so then they do quenching. What is the purpose of quenching? They want, so if you slowly cool, it forms Al2Cu, CuAl2. But if you quickly quench, it means even though it is it will try to form a CuAl2 at this temperature, but you have quenching means quickly quench, heat it and place it in water, quickly drop in water. It means even though it is trying to form CuAl2, you have not given enough time for this for the formation of CuAl2 quickly. So even after at room temperature also you will get a single phase only. But here alpha is in metastable condition. Then what they do? Then they do edge hardening. Then after from this condition, what they do? They heat it at any temperature between either here or here or here or here. Any temperature they heat. When they heat, what will happen? Here your microstructure is something single grain, alpha, alpha, alpha. Now when you heat any temperature, what will happen? On alpha you will get Al2Cu, theta precipitate. On alpha you will get theta precipitate. On alpha you will get theta precipitate. When you cool here, what will happen? Heat here, what will happen? It will try to dissipate the precipitate. So during quenching you would have created a lot of vacancies. So these, when you again heat it at a particular temperature, that is edge hardening treatment, what will happen? The precipitates, the cluster of copper and aluminum, this is phase diagram of aluminum copper phase diagram. Cluster of copper and aluminum will go and sit in the vacancies and it will form throughout the microstructure, something like this. And this particular precipitate size determines the mechanical properties. Now suppose you have microstructure 1, this is microstructure 2. If you do tensile testing for this material, what will happen? For microstructure 1, when you do tensile testing, what will happen? When you do tensile testing, you will get what? So microstructure 1, during tensile testing, what will happen? The dislocations will move above the yield point because plastic deformation zone above elastic limit. Then the dislocations will move from one grain boundary to other grain boundary along the slip plane and slip direction. And while dislocation can move easily because there is no obstruction in the case 1. In case 2, what will happen? Case 2 has already this kind of microstructure. Now the dislocations are moving from one grain to other grain, and in between there are the microstructure precipitates are there. These precipitates are hard particles. So what will happen? Wherever precipitates will be there, this precipitates will obstruct the dislocation motion. As a result, the dislocation cannot move further. And to overcome this motion, when can it move further? Suppose this is the size of the particle. Whenever the dislocation will break this particle into two pieces, in that condition only dislocation can move. So for breaking that particle to two pieces, you need to apply high stress. So strength of the material will be high. Similarly, in this treatment, they keep on increasing the precipitate size bigger and bigger and bigger. If your precipitate size will be bigger, means you will have more obstruction, more hard particles. So your material will be very, very high strength. Now there is a critical size above which it will not further strengthen. If the size will be very, very big, then this will not able to move. This will not able to obstruct dislocation motion. Dislocation, in that case, what will happen? Dislocation cannot break this big particle, it can bypass. This is called as bowing, and again it will move. So in this case, strength will again reduce. So in this edge hardening, what they do? They get a peak condition. So at a particular temperature, they will get like this. This is, suppose this is strength, this is time. At a particular edging temperature, suppose here, you will get something like this. So this is your peak condition. What they do? They impart that particular heat treated condition and supply to the customer. Then what happens? The customer gets a material with this kind of microstructure, a critical size of precipitate. And to obtain this microstructure, what they do? To obtain this microstructure, they do a particular heat treatment. What is that heat treatment? We discussed solution treatment, quenching and edging. For example, for a 7000 series alloy, they do this edge hardening treatment to 120 degrees centigrade, to 24 hours. Then only they get this kind of microstructure. And this microstructure gives high strength. Now, when you do this kind of with this microstructure, when you do welding, what will happen? In the heat affected zone or anywhere, you will because of the temperature, we want 120 degree 24 hours. They have done that and supplied. Now in welding, what will happen? In the fusion zone, it has disturbed this precipitate. At high temperature, this precipitate will again dissolve in the matrix. Then you purchased this material by giving high money, but you end up with, during welding in the weld zone, it will dissolve because the temperature will be, this stability of this temperature is around 200 or 300 degrees centigrade. So your temperature is more than 200 or 300 degrees centigrade because you melted and solidified. So even though you purchased high cost to get this kind of microstructure, during welding in the weld zone, your microstructure will not like this. This precipitate will dissolve and your microstructure will be something like this. It means during welding, your temperature will come like this. Because the melting, if you do melting of aluminum melting point is 660 degrees centigrade. Now at the heat affected zone, it may be around 550. In 550, you will get this kind of microstructure. You are getting, no? Single phase. So single phase will not give edge hardening effect like this. So this is not, that's why this process is not suitable for edge hardenable alloy. So next one is for dissimilar materials. When you want to join dissimilar materials, for example, if you want to join aluminum with steel. If you join aluminum with steel, you can see this phase diagram. This phase diagram says that, for example, if your alloy composition is this much, you are getting Fe3Al. If this one, you are getting one phase diagram, one intermetallic compound. So at different alloy percentage, you are getting different type of alloy, different type of intermetallic compound. You can see Fe3Al, FeL, Fe3, F2Al7, FeL2, and this intermetallic compound forms at the interface of the between two joints. Yes or no? How to join aluminum with steel? When you want to join aluminum with steel, at the interface, temperature will be very, very high. So you can see any temperature you get this kind of phase. Even higher than this, you are getting this phase. So temperature is high, so there is a high chance that you may get any kind of intermetallic compound. And these intermetallic particles are brittle. So whenever you have this kind of intermetallic at your interface, then when you do testing, then crack will start at that interface of the intermetallic particle and will propagate very easily. As a result, you will get very low joint strength. So that is not desirable. That's why That's why you get very limited mechanical properties in fusion welding processes. So we discussed that in fusion welding process we have lot of demerits like wide heat affected zone, casting related defects, low mechanical properties, residual stress and distortion related issue, not suitable for edge hardening alloys, and you get intermetallic formation at the interface. Due to this, fusion welding is not popular, even though it is these are the easy process, but it gives lot of demerits. So that's why a lot of research work is going on to develop joints by using less heat input. So that's where both solid state joining is very important, plays a very important role. How to reduce these effects? If you do joining by inducing less temperature. If you do joining by less temperature, you can overcome heat affected zone problem, you can overcome the low mechanical stress problem, you can overcome the residual stress problem. Okay, you can overcome this one. Okay, you can overcome this one, but you cannot overcome casting related. So casting related, if you do join, casting related problem will be overcome if you don't melt the material. Casting is a melting and solidification, so that kind of defect will not be observed. You don't melt material. So that's why solid state joining processes are very important, because in solid state welding processes you don't melt your metal, and whole joining is happening in solid state. So now our next part is solid state joining. So our next process is solid state welding process, which I am going to discuss from now on. So in solid state joining process, the joining takes place without fusion. In solid state joining process, the joining takes place without fusion. There is no liquid phase in the liquid joint. That is the main advantage. So it's joining is happening without melting. So since the base metal doesn't melt and form nugget, the metal being welded retains their original property without heat affected zone problem associated with fusion welding. In fusion welding, you get heat affected zone problem because one was melting, and so heat transfer was happening very high. So near the molten part, you are getting a very big high heat affected zone problem. Here, since you are not melting, so the heat affected zone problem can be nullified, or even though if heat affected zone will be there, its content will be very less. In any fusion welding process, you mainly use filler materials. In solid state welding process, filler materials are not used. So these are the merits of solid state welding process. So there are different kind of solid state processes. One is few are diffusion based processes, few are deformation based processes. So solid state joining process are of two types. One is diffusion based, second one is deformation based. Okay, so first one is diffusion based, second one is deformation based. In deformation based, you have various types like cold welding, offset or butter offset welding, forge welding, roll bonding, ultrasonic bonding, explosion bonding, friction welding, friction stir welding. All are like your deformation based process, and diffusion welding is your diffusion based process. So let us recap our welding. How welding is possible? How does welding happen? We have already discussed in our earlier class. We discussed that welding is possible when mating surfaces to be welded will have material continuity. In order to get material continuity, we have to place the mating surfaces within equilibrium interatomic distance. So we discussed in the last class. It means if you can maintain the two atomic layer at less than equilibrium interatomic distance, welding is possible. Okay, so that's what we discussed. We discussed that if this is atom A, material B, if you bring them both to the interatomic distance, then welding is. We also discussed that how to maintain material continuity equilibrium spacing for a weld. We said that for that we need to clean the surface, and we need to bring the atoms in the mating surfaces together in large numbers to overcome asperities. This one we discussed in the last class. Then we told that there are three mechanisms to maintain material continuity. One is melting and solidification, second one is solid state plastic deformation, third one is fusion, in which we have all in a fusion welding process. In fusion welding process, this material continuity can be maintained by melting and solidification. However, in solid state joining process, still you have to maintain that continuity, right? So you are not hitting. So how can you do? You can do a very high plastic deformation. You plastically deform the material in such a way that the two contact surface will come as close as possible, and the distance between both will be less than the equilibrium interatomic distances, so that you can get joining. So that is one part. That's why this is coming under deformation based processes, which we discussed. We told that solid state processes are of two types: deformation based, and second one is diffusion based. Second one is diffusion based. In diffusion based process, you have to clean two surface interfaces very cleanly. You have to remove all the unwanted particles like asperities and gas bubbles and everything, oxide layers, everything. Then you have to keep as close as possible. Then you have to apply heat. When you apply heat, what will happen? Atomic diffusion will happen from one metal to other metal, and as a result, from A to B, suppose you want to join two pieces, then atomic diffusion will happen from, if these are the atoms, then atomic diffusion will happen from like this as well as like this. So at the interface, you will get atoms of AB, AB, AB. It will form like a alloy. If this is A, this is B. So because of this diffusion, you get solid state welding. So this is called a diffusion based process. So we discussed solid state welding can be classified into two types. One is deformation based process, where you need to do severe plastic deformation to maintain the material continuity. Second one is diffusion based, where you don't want to apply very high force, but you need to clean the surfaces very properly. Then you have to apply force not to deform, but to keep close contact between two pieces. Then in this condition, you have to apply very high temperature in such a way that atomic diffusion should happen. Atomic diffusion should happen from one phase to other, one substance to one interface to other interface, one material to other material. As a result, you will able to joint at the interface. This is the phenomena of solid state process. So in solid state process, how can welding happen in solid state welding? In solid state welding, if you see SSW, S means solid state welding. If I give SSW, SSW can happen due to coalescence of interface. It means, what is the meaning of this? This meaning is material continuity. So in solid state, what will happen? Suppose this is A, this is B, then at high temperature it will be diffused, and here you will have concentration of A and B. This is this part. Okay, so this part can happen possible due to application of pressure, temperature, or so. What do you do in solid state for solid state welding process? You have to make, what are the steps? Steps involved are, first step is clean the surface, clean the interface. Second one is, when you clean the interface, you can remove the unwanted part, but when you zoom it, in this area, if I zoom at the interface, as I said in the last class, what did I tell in the last class? Many materials are there like aluminum, magnesium and all. When you keep even in room temperature, what will happen? In the atmosphere you have oxygen, hydrogen, nitrogen and all. The oxygen will come and react with the top surface of aluminum, and it will form aluminum oxide. So on the top of your aluminum, you feel that you have purely aluminum, but on the top layer you will have an aluminum oxide layer. Similarly, if you take magnesium, if you keep magnesium, suppose you clean your magnesium before joining and keep it in atmosphere for 5 minutes or 10 minutes or a day. So that is enough for reacting. So then during that time, what will happen? This top surface will react with oxygen, and a magnesium oxide layer will form on the magnesium plate. Now, after cleaning also, when you want to join solid state joining means what will happen? Either it will be deformation based joining or diffusion based joining process, isn't it? So for whatever it may be, what will happen? You have to, for a deformation based joining, you have to apply load, pressure in such a way that here in this zone plastic deformation will happen, so that mating up between two pieces will happen. If it is a diffusion based process, then also you have to make in contact and apply high heat, high temperature, so that atomic diffusion will happen from one layer to other layer. This is the difference between diffusion based process and deformation based process. But before that, atomic, you should get atom. If this is A, this is B, A and B should meet here. But actually, if there is an oxide layer in the surface, then this is oxide, this will be oxide layer. You have to remove this oxide layer first. Therefore, sample preparation is very, very important. Surface preparation. Surface preparation is very important in any kind of solid state welding process. First, you need to clean the surface, then you have to prepare the surface, because then if you have oxide layer, how to prepare? You have to use emery paper, remove the top layer, then you have to use some blasting, grid blasting, or something you need to do to remove the top part, top layer. Okay, that's why surface preparation, or by using some steel brass or iron brass, you try to remove the oxide layer. So surface preparation is very, very important. That is the next step. Then the third step is either deformation based or either induce deformation or diffusion. If you induce deformation, this process is called a deformation based process. If you induce diffusion, this process is called a diffusion process. How will you induce deformation? Apply very heavy load, apply high compressive load or tensile load, apply high load. How to get diffusion? Apply high temperature. So as a result, what will happen? Suppose you want to join these two plates, you apply load, and make such a way that it will join together. Then apply severe load, and diffusion will happen at the interface. You will get a metallurgical joint. Or you apply high temperature so that diffusion will happen at the interface, and you will get a joint. So this is the principle behind solid state, any kind of solid state joining process. What is the essential requirement for successful bond formation of solid state welding process? First, as we discussed, the fairing surfaces must be free from impurities. That's why I told the first step is cleaning. Second step is very close intimate contact between fairing surface for atomic interaction. So you have to bring both to very close contact. That's why what I told, I told surface preparation, and then you have to apply high force in both sides so that both will come in contact with as close as possible. When the distance will be like your lesser than your equilibrium equiatomic distance level, then joining is possible. What are the advantages of solid state joining processes? Parent materials essentially retain their original properties, so there will be no parent material will not lose any property, because whole joining is happening below the melting point. So heat affected zone problem can be significantly minimized. Next one is wide materials including dissimilar materials can be joined. We discussed that it is very difficult to join dissimilar materials in fusion welding process because of what? Because of many differences. If you use fusion welding process, and then we saw that there is high chance the intermetallic formation forms at the interfaces. That is first demerit. Second demerit is very difficult to join two pieces because of difference in coefficient of thermal expansion, because of difference in thermal conductivity, because of difference in melting point of two materials. It is very difficult to join because the temperature is very, very high in one case to other. So, and you want to melt above the melting point of your material. So all these things can be minimized in case of solid state welding process. So you can easily join two pieces by using dissimilar metals by using solid state joining. Since the temperature is less, joining temperature is around 500. If it is aluminum alloy, your joining temperature will be around 400, and the room temperature is 30 degree centigrade or 27 or 30 degree. So the difference is very, very less. So you will have less chance of residual stress formation or distortion formation. Even though it will be there, but it will be less. Okay, so environmental safety and those things are there. These are the advantages of solid. Now, so since we discussed, there are two kind of solid state processes. One kind is called as diffusion based solid state process. Second type is called as deformation based solid state process. The first type is diffusion based solid state process. What you have to do, what you need to do in diffusion based bonding based solid state process, you have to take, suppose you want to join aluminum A with aluminum B, then bring two workpieces together, then apply load from both sides. When you apply load, what will happen? It will before that you do the normal procedure. What is the first step? Clean, do surface preparation, then apply load like this. What is the objective? Here your objective of applying load is not to deform, your objective is to bring two pieces as close as possible. That is your objective in applying loading. Then fourth point is apply high heat, or temperature. Then you give temperature. When you apply high heat, what will happen? Diffusion will happen. So here also you will have atoms. Here also you will have atoms. When you give high temperature, it will happen at this time. During that time, what will happen? Atomic diffusion will happen from here to here, here to here, here to here. Similarly, here to here. This. Then when you apply load, then what will happen? Atomic diffusion will happen. Atomic diffusion will happen, and as a result, you can see diffusion of B atoms will happen. It will go from bottom to top B, and A atom will move like this, and as a result you will get, you can see this zone is mixture of A plus B atoms. You can see mixture of A, B atom will go like this, B atom, and A atom will come like this, A atom will come like this. So you will get a mixture of A and B atom in this zone. You can see you are getting a mixture of A and B. This is A atom, red is B atom, A atom, red is B atom, like that a mixture you will get, and like this diffusion bonding is happening, and it is happening based on Fick's law. You can go through your Fick's law equations, and which depends upon the diffusion coefficient and all, and based on the Fick's law the diffusion is happening. So please follow the from book Fick's law, Fick's first law, Fick's second law, and you can correlate this diffusion kinetics with the Fick's law. Now because of time limitation I cannot go to discuss in detail about that. You can go through from book. So like this you can see initially this is A, this is B. So initial contact, then when you apply load, and because of diffusion finally what will happen, you will able to get a single grain. There is no interface. This is your diffusion bonding. So what are the key features of diffusion bonding? The diffusion bonding is a solid state diffusion process. Here the diffusion temperature lies in the range of 0.5 to 0.7 of melting point. MP stands for melting point. So in diffusion bonding, the melting temperature, the bonding temperature is 0.5 to 0.7 of times the melting point. If you want to do aluminum diffusion bonding of aluminum, then what temperature you have to hit? You have to hit in this range. Aluminum melting point is around 660. So your heating should obtain between 330 is half of the melting point to higher, to around 400. So in this zone you have to do heat treatment so that atomic diffusion will happen. The condition is high temperature, pressure and time. So you have to apply pressure only to bring two workpieces to as close as possible. That only you have to do. No deformation is possible requirement. So the pressure is a firm squeeze, no deformation. You should not apply pressure to deform the material. This is not a deformation based process. This is a diffusion based process. You need to apply only up to bringing both materials together as close as possible. Up to that level you have to apply pressure. Then you have to use temperature to do that. Since you want to generally this process is done under inert atmosphere like argon or helium atmosphere, so that other atmospheric gases will not come in contact with your workpiece material. So and the diffusion mechanism is based on the vacancy migration or the substitutional migration. So when one atom is shifting with other atom, suppose B and A atom, B is coming and sitting in A place and A atom is going and sitting in B place, then that is called a substitutional atomic diffusion. Okay, there may be some vacancies also. If one atom will come and sit in the vacancy, this is called as vacancy based diffusion. Okay, so the diffusion is either vacancy based or substitutional based diffusion. And what are the key advantages? The key advantages are filler materials are not used, and heat affected zone is very less, and here since the temperature is very less, so can bond metals and ceramics. Metals, you see, ceramic is one kind, metal is one kind. Even you can do that also by using this, and you can also easily do similar and dissimilar materials like aluminum with copper, copper with steel, steel with aluminum, steel with titanium. Anything is possible for joining. So what are the limitation? Limitation is since diffusion, so imagine diffusion takes long time. Unless complete diffusion unless completion of complete diffusion, you cannot stop the process. So how diffusion is happening? You saw this one, no? Initially it will diffuse, the two layers will diffuse, and finally here complete diffusion has happened. So up to this stage you have to wait. So it takes long time for diffusion to complete diffusion to occur. Sometimes it may take a day, sometimes it may take a week, sometimes it may take an hour, like that. From seconds to hours, it takes long time. That is the main limitation in diffusion process. So for higher temperature, the time will be less, completion of diffusion time will be less. For if your temperature is low, the time of diffusion rate will be high. The complete diffusion will happen at high time, long time. It will take long time for diffusion. Next type is deformation based process. In deformation based process, what you do? You apply both together. Both in deformation based process, first is you apply deformation. You have to use deformation by using heavy loading in such a way that you will bring two pieces together, as well as you may apply temperature also, but this is not compulsory. But mostly used. So in deformation based processes, the two material continuity will be obtained because of plastic deformation, so that joining happens, and temperature is also required. So less temperature and high level of deformation, both things are happening together, but temperature is not mandatory. For example, in cold rolling, cold bonding, temperature is not required, but mostly temperature is also used for deformation. So mainly deformation based processes, 90% of joining is 70% of joining is happening because of deformation, and remaining part of joining is happening because of diffusion. Okay. So here no melting occurs, but it will be hot. No, plastic deformation is required. Plastic deformation required in the interface. So works with metals only, since you need ductility. In the previous case, diffusion bonding process, you can join metal to ceramic because plastic deformation is not required. Here you have to plastically deform the material at the interface. So the material should have ductility to obtain that deformation. So if you use ceramic is having very low ductility. So ceramics cannot be used. So only metal can be used to join. So only metal to metal joining is possible. You can do any kind of dissimilar configuration, aluminum to steel, steel to copper, copper to titanium, titanium to aluminum, like that you can do. But it is very difficult to join aluminum to ceramic, copper to ceramic, like that, because ceramic is brittle. So you cannot provide the plastic deformation like this at the interface. So that is the limitation here. So there are these are the different kind of type of deformation based processes. As I discussed, like your arc welding process, all the processes are almost similar. Similarly, all the deformation bonding based processes are all almost similar. Okay, each process gives you one kind of plastic deformation. How are we inducing the plastic deformation and diffusion both together? So first one is butt welding or offset welding. Second one is forge welding. Third one is roll bonding, ultrasonic welding, explosion welding, friction welding, and friction stir welding. What we will do is, we cannot go in depth in each process. I will quickly go through each process because the principle is same in all the processes. So I will go through one by one. First one is butt welding. So it's a very simple process. In butt welding, it is a deformation process. You slightly heat and apply pressure. With very high apply pressure, you can able to join the interface like this. This is your simple offset or butt welding. Second one is forge welding. A forge welding, mostly they use in blacksmith shops. What they do? They heat a metal piece at very high temperature. Then they hammer it. By hammering, they change the shape of the material. Like they heat the material to make the material soft. Then they apply very high load force to get the shape like this. So you can see, no, the chisel, the tool of hammer, those things they prepare by this forge welding. It's a common practice. You might have seen in this kind of thing in any smith shop, blacksmith shop. They heat the metal, they apply very high load, and by doing that they weld two pieces together. That is called as forge welding. Next one is explosive welding. In explosive welding, what they do is they take two materials. Suppose you want to join two materials. These are the two materials, material A and material B. So then what they do, they use a rubber pad. This is a rubber pad or something. Then on top of it, they use explosives. What they do? The two pieces to be joined will be kept like this. Piece 1, atom A, B. You will pay at some angle. You have to maintain some angle. Place both materials to be joined at some angle. Then use a rubber pad or something, and on top of it you use explosive. Then what happens? Then explode. Since you have explosives, explode. Use fire and explode. Due to explosion, what will happen? This top part will come in contact with the bottom part at very high velocity because of this explosion. You are taking two pits together, you are keeping like this, then you are placing your explosive on top of the top plate, then you are exploding. Because of explosion, what will happen? The top part will hit the bottom part. The top part will hit the bottom part at very high kinetic energy, very high speed. So what will happen? Whatever oxide layer will be there in the bottom part and in the top part interface, because of this heat, it will form a it will explode. It will go out from the material. So there is like a jet. It will form like a jet, and it will come out. Those oxide layers will come out because of this velocity, and it will come out from the workpiece material. And these two fresh pieces will be joined together within very short time. So this is a well established process, widely used process. Many places they use this process to join two pieces. Here joining is not happening because of diffusion. Joining is happening because of deformation. Diffusion has not happened. Atomic migration has not happened from one piece to other piece. How joining is happening? Because of the mechanical interlocking. When it has happened very fast, so because of that, interlocking happened at the interface. Because of mechanical interlock, it joins. So this is your joining process. Sometimes because of that high impact velocity, the material also partially melts. So some zones you will get diffusion, melting and solidification, but mostly it will be mechanical bonding, joining, because you cannot get diffusion because time is very less. For diffusion to happen, if you see Fick's law, time is also a parameter. So for diffusion to happen, you need some time. So here time is not enough. So your joining is happening because of mechanical interlocking. Okay. So the advantage is any pieces can be joined. So what are the applications? There are a lot of applications for this explosive welding. You join them, get many components in aerospace, heat exchanger, bimetallic cladding, ship structure, corrosion resistant, chemical process tanks, household utensils. These are the utensils you can see. These are of made up of this bimetallic joints are made up of explosion welding. What they do? So the two pieces to be joined are, as I said, they keep two plates together, join it. Suppose you want a let us say the aluminum copper bimetals. So many places in spacecrafts they use aluminum pipe with steel pipe, and aluminum pipe to steel pipe joining is really a challenge. It's very difficult if you want to join both by using fusion welding process, because like the limitations I have already told you. So for that, what they do, they take a aluminum piece, they take a steel piece, keep the steel piece below, and top of it they keep aluminum plate. Then on top of the aluminum plate they use explosive. They use rubber only to prevent this explosion to contact with top plate. That is only the purpose. So on top of the aluminum they use explosives. Then they do it in a remote place, go to remote place, and then blast. They explode the explosive. Then aluminum will come, aluminum ductile material. Aluminum will come if you use aluminum steel joint. Aluminum will come and hit the joint, steel joint. Then joint will happen like mechanical interlocking. Then what they do? They machine out the like your bimetallic component, because you want to join steel to aluminum pipes. So they want to get, suppose you want to get a sheet of 6 mm length pipe of 3 mm diameter, 3 mm diameter, 6 mm length pipe of aluminum steel. Then what they do? They machine from this zone. then there will be a bimetal. Bimetal means one side will be aluminum, other side will be steel. Then they provide nut and bolt thread arrangement, then fix aluminum side to aluminum and steel side to steel. Like that they can obtain, steel to aluminum join in spacecrafts. It's a very well established technology. It's a commonly used. What is the main demerit? The main demerit is that you have to do in a remote place because explosion. No, the applications are there. What are the advantages? Large surfaces can be obtained, very like your this room or a big roof. That kind of surface also you can do. What you have to do? You have to take that, place that roof, then place this one more layer which the plate which you want to join, that you keep in the top plate and then explode. So size is not a matter. Any size can be joined by using this process. High quality of bonding, low cost, and it's not. This is not a low cost, and surface preparation is not required here because joining is happening because of interlocking. And even though if you have oxide layer, by oxide layer it will be easily removed because of that high velocity, right? So that is oxide sample surface preparation is not required. So the disadvantage is like brittle materials are difficult to process because it has to impact and mechanical because of plastic deformation happening at the interface. So you are getting joint. If it is a brittle, it cannot sustain that high impact load, so it can fail. So brittle material are not possible. Only simple safe parts can be bonded. Thickness of the flyer is limited. Yeah, and the main thing is safety and security aspects. So because you are dealing with explosive, you cannot explode in a normal atmosphere. You have to take in a remote place, do this process in a remote place. That is the main limitation of this process. This is about explosion welding. Next one is roll bonding. In roll bonding, what are the steps? In roll bonding, generally we use rolling machines. High capacity rolling machines are being used for making roll bonding sheets. So generally, this by roll bonding you get bimetallic sheets of different applications. Aluminum to copper bimetallic sheets or aluminum to steel bimetallic sheets. It's a being wide application. So what they do? They prepare surface. Suppose you want to join two pieces like this, then you have to surface. What is the role of surface preparation? To remove contaminants like dust, absorbed gases, water vapor and oxide layer. Then after removing the surface layer, you have to scratch, brush to provide work hardening for sound bonding, to provide the work hardening of the material as well as to clean the oxide layer of the material. You have to clean, you have to scratch the whole material by brush. Once it is happened, then you have to place two pieces together. Then you have to place the both pieces against a rolling mill between two rollers. Because of that, you will get compressive force in this zone, and you will get a bond properly. So you have to apply very high plastic deformation. For example, 50% reduction per pass or 60% reduction per pass. Then only bonding will happen at the interface. So there is a wide application is there for roll bonding. They use bimetallic coins. You can see coins are widely used by using roll bonding. Bimetallic bushes are used. Aluminum copper made up of aluminum copper. They make sheets and they bond, roll it and join. Then electronics also, a lot of applications, switches and control panels they use. Household application, they use copper with aluminum. You can see outer part is copper, inner part is maybe steel or aluminum. And they use solar panels. They use decoration components, and many places they use they make the bimetallic components by using roll bonding process. Next one is ultrasonic welding. In ultrasonic welding, what they do is they take two pieces. You have to take two pieces to be joined, and then simultaneously apply load as well as frequency, oscillate. So by using a transducer, you can oscillate the whole thing at very high frequency. You have to apply very high frequency and you have to apply load. So because of this, deformation is happening at this interface. At the interface, you can able to get a joint. Again, I will repeat. You have to keep two pieces together. Then you have to apply force, heavy force, as well as under the application of force, you have to apply very high frequency oscillation. You can use for that. You may use some transducer for oscillating the workpiece. By using transducer, you can oscillate. And because of this oscillation, a vibration is generated at the interface, and because of that vibration is happening under the application of load. As a result, you are getting deformation at this interface and bonding is happening because of that. So the features are excellent to all materials. Dissimilar metal can be joined with wide range of metals, capability of weld through oxides and contaminants. So all the things, but the limitation is like it should be a ductile material, because you are again deforming at high frequency. So the material should be have high ductility, and you can only do in lap configuration. If you want to join in butt configuration, it is not possible. You can only do in lap configuration. This is about ultrasonic welding. Next one is same friction deformation based processes can be done by using friction based application. So here friction will induce temperature and deformation also. So there are few deformation based processes where friction is used as a heat input. So in deformation process also you have to give some heat input. In the friction based processes, deformation will happen as well as friction will also be imparted to the material. So because of the deformation and friction, you get joining. So one kind is friction welding, second one is friction stir welding, third one is friction stir processing. First we will discuss about friction welding. In friction welding, what happens? In friction welding, the two pieces to be joined will be brought like this. Then what you have to do? You have to rotate one piece will be stationary, and other will be rotated. Then the rotational piece will be brought. Rotational piece will be brought and it has to touch the stationary piece. Then in rotational condition, then what will happen? Because of friction, lot of friction at the interface, it will soften the material. Once it softens the material, in that condition you apply load. Once you soften the material, in that condition you apply load. When you apply load, what will happen? So what will happen here at the interface? As I said, any material whatever you do, interface you will have oxide layer. So and you don't want that oxide layer. So that's why this process is the best process, where sample preparation is also not required. You have to bring two pieces together. One will be in rotational condition. In rotational condition, you have to bring it down. You have to rotate against the stationary piece. Then it will soften the adjoining this interface. When it will soften enough, then you have to apply force. When you apply force, what will happen? This area is already softened, this interface. When you apply force, this metallic material in this region will be flashed. It will come like this as a flash. It will come like a flash. So that is nothing but at the interface. This interfacial area will come like a flash, which is nothing but your oxide layer. So this flash has come out like your oxide layer. Now what will happen? Now your fresh material without having oxide layer will come in contact with each other. Element A will meet with element B, and without the presence of oxide layer, because of the compressive force, the oxide layer it was the soft condition, oxide layer had come out like this. So it is a fresh material now. Then you apply pressure again. Apply pressure, stop rotating. Now stop rotating and apply pressure. As a result, you will get a joint at this particular intersection. So this is called as friction welding. So there are different kind of friction welding. This is called as radial or orbital friction welding, and by using this kind of process, you can join any type of symmetrical components. Okay. It is having wide application. You can there are three classes. We discussed about this class. This is called as rotary friction welding, where you induce friction between two parts together. That friction softens the interface. Then you apply force to obtain the deformation. So you applied friction to soften means to induce heat at the interface. So here the friction welding is a simultaneous application of heat and deformation. Heat was given because of friction between two mating surfaces. Then deformation was given because you gave compressive force, so that joining happened. So because of that, joining is happening. So this is one class is called rotary welding. The linear friction welding also, you have to do linearly rub two pieces together to induce friction. Then you have to apply compressive force to join together. Third one is orbital motion. Here also you can arbitrarily do and you can get your component. So one classic example is your twist drill bit. So there are so many applications of friction welding. It can be joined for any material to any material. You can see this example: aluminum to steel, steel to aluminum, anything to anything can be joined. You can see some Typical example, this is a drill pipe they do by twist drill. Here this is your drill bit and this is your shank, drill bit shank. They join here by using friction welding. So this is a universal joint. Here they join by friction welding. Here gear hub they join by this is your friction welding. So this is your bimetallic engine valve. They joined here by friction welding. So it is having huge application. You can see many applications. Electrical connectors, pump the details, and piston rod. Here they join by friction welding. So friction welding has huge lot of applications. So the last category is friction stir welding and friction processing. In friction stir welding, what you do? The two plates to be joined. Suppose this is a plate A, plate B. So friction stir welding. So where friction stir welding. Friction stir welding can be used to join two plates mostly in butt configuration. You can also do in lap configuration, but mostly in butt configuration. Any length you can do. You can also do in different configuration as well. So what you do, you bring two pieces. Suppose you want to join two pieces. Suppose this is your plate 1, this is your plate 1, and this is your, now you want to join two pieces. So bring two pieces and join together, place like this, place these two pieces like this. So this is my A, B. I want to join at the interface. What do I have to do? I have to place these two plates like this. Then I have to bring a non-consumable tool. So tool will be something like this. I will have a tool, and this area is called as tool, and this area is your solder. And tool may have either this will have a taper cylindrical, or you will have in it will have something like some solder, some threads will be there, or in your tool you will have your tool, like this is solder, this is tool. Your tool may have square, or your tool may have some triangular interface, anything it may be, depending upon your requirement. You have to design your tool. You have to mainly they maintain the solder ratio is 3:1, solder diameter and tool. So solder plays a major role, tool plays also a major role. So depending upon your requirement, you have to design your tool. And the tool length, tool depth or tool length depends upon your thickness of your material. Suppose the thickness of your material is 3 millimeter, then the tool length should be around 2.8 millimeter or something. So like that you have to design your tool. Then bring the tool, place somewhere, place between at this interface. Suppose you want to start from here. Suppose you want to start here. So keep your tool here. Bring here and place your tool here. Then what will happen? Before bringing, what you have to do? You have to keep two stationary plates. Bring the tool. Before bringing down the tool, rotate the tool. So generally it is in friction stir welding you will have a machine. Like the machine will be like your vertical milling machine. Okay, so you will have a vertical spindle, and on this spindle you have to mount your tool. Vertical spindle you have to mount your tool, and on the bed you have to mount your workpiece. Okay, then you have to, after mounting your tool on the vertical spindle of your friction stir welding machine, then what you have to do? You have to switch on. We have to rotate the tool. So you have to rotate the tool, and in rotational condition you have to bring the tool. In rotational condition you have to bring the tool and plunge the tool between two solid interfaces. At one point you have to plunge. The tool has to come. It will be plunged here. Then still it will be in rotational condition. So in rotational condition, the tool will be brought from the top to the inside the tool. Okay. So then the whole thing, suppose the thickness is 3 millimeter and tool length is 2.8 millimeter. Whole thing will be plunged to the tool. Then what will happen? Then you have to keep it for some time. What is the purpose of keeping that for some time? Because at the adjoining area you want to soften the material. So now imagine you have two solid pieces. At near the solid pieces, the tool is rotating. A tool is rotating So because of this rotation, a friction is generated and the adjoining area near that area, the material will be soft. What is happening when you brought your tool and kept inside, the material which is contacting the tool, what will happen? It will, apart along with the tool, the material will be also moving and depositing in the bottom layer. So like this continuously it will happen, and you have to allow that for some time, let us say 1 minute. So rotate the tool, bring the tool down, keep it, insert it inside the two workpieces, then again still allow it to rotate for around 1 minute. Then whenever you feel that the adjoining area became soft enough, then what you have to do? Then you have to move the tool. Then in that condition you move the tool in this direction. Move the tool in this direction. Then what happen? At this zone, what will happen? The material whichever, then what will happen? The tool will rotate in rotational condition. Then what will happen here? Because of plastic deformation, joining will happen. The material will come out along the tool. If you take a point, in this point, when you have a one rotation, the material will come out, rotate one side, and it will be deposited behind it. So as a result, when you go out and remove the tool, you will get a hole. That is the advantages of friction stir welding, because you will get a hole at the end. So otherwise the process is very good. So since plastic deformation is happening significantly near this, so you are getting grain refinement as well. Your microstructure will have refined grain as compared to your base material. So you will get high joint strength in this case. Your generally in any welding process, your nugget region or weld region gives low strength and base material gives high strength. That's why you get some joint efficiency. Joint efficiency is around 60 to 70%. However, in friction stir welding, since grain refinement is also happening at the interface, at the joining region, so because of severe plastic deformation, grain refinement also occurs at the joining region. Since the grains are smaller than the base material, so strength inside the friction stir zone is very high as compared to the base material. That's why the joint strength in friction stir welding is very high. That's why a lot of research work is going on in this process, and this process is the newest joining process till now. So you can see this one. So you have to keep two pieces together, bring the workpiece, bring the tool, plunge the tool like this. Then it will become soft. You can see the hot thing. No, this is become soft. When it becomes soft, you have to remove the whole thing, and you can end up with joining like this. So what is happening when you get a cut section? You are plunging the tool and you are rotating. So what is happening because of that? Because of this plunging, you are giving forging action to the workpiece, and then you are dragging the whole material in this direction. So this is your extrusion. So both things are happening together, forging and extrusion. Because of that, you are getting severe plastic deformation just below the workpiece. So because of this forging action, the solder, what does the solder gives? Solder gives forging action. And what does the tool gives? Tool is dragging the material ahead. So tool is giving extrusion action. So because of forging, because of solder, we are giving forging action to the tool, and as a result, it is inducing a lot of heat input. And because of tool movement ahead the workpiece, so that gives you the extrusion action. So because of forging and extrusion action, the material becomes severe plastic deformation, and as a result, you get refined grains. Okay, so these very good properties. If you see the microstructure, so for example, we took a microstructure and at this around this zone. So throughout we got uniform microstructure. You can see the microstructure in the friction stir welding zone is very fine grain. However, here the microstructure is of coarse grain. So this data was taken from a review paper which was published in Progress in Material Science by Professor R.S. Mishra, Rajiv Mishra. I have taken this data. I have not cited this data here, but I have taken this information from that review paper. Okay, so generally for different materials, you need to use different tools for friction stir welding. This is about our solid state welding processes. So today we discussed about resistance welding and solid state welding processes. And in solid state welding processes, we used many diffusion based processes and deformation based processes. So today we discussed up to this. And next class we will discuss our defect analysis and metallurgical analysis of welding. So next class we will discuss about welding analysis. So whether anybody want to have some interaction? So next class we will discuss about liquid solid state joining processes, and weld defect analysis.